So we have looked at many of the data types, right? And you know, I think we have taken some examples also. Mm, then I have told you about the difference between four-state and two-state variables, about between packed and unpacked arrays, and see, there may be a few things that I may have forgotten to mention, right? So let us look at this is something that sometimes may be useful to you. Okay. See, we know about equal to, right? So that sort of makes sense when all the bits are zeros or ones, right? Sometimes, X and Z values may be present in those values, right? So then you should use this one. So I'll quickly illustrate this. Suppose we have logic 3 to 0, 4-bit 10ZX. Okay, so I am assigning 10ZX and logic okay. So initially X is set to 10ZX and Y is set to 4 bits X 0 1 1. Okay. Let us try if X equal to Y, then display X and Y are equal according to equal to equal to. If X equals Y, then display X and Y are equal according to okay. So this is a wild comparison. Maybe I have not mentioned this before. Right? So if you try running this, If you try this, see x and y are equal if you go by this comparison. Okay. If you go by strict comparison, it will say these are not equal. One of them has a 1, the other has an x. One of them has a 0, other than. So 0 is matching. Um, these x's are not matching, z is not matching. But if you go by wild card or wild comparison, they will be considered as the same. Okay. So sometimes this may be useful. So when you use this wild comparison, even z and x, they will match 0 and 1. Okay. If this was 1, of course, they will not match. Okay? If this is 0 and this is 1, then they will not match. So nothing will be matched. Okay? So no statement came that they are matching. Is that clear? So that is one thing that I may have missed. And I'm trying to see what is the small things like this that I may have forgotten to mention, which may be useful sometime. Um, Aliasing is something that is sometimes useful. So let us look at aliasing. So here, okay, there is some question. Yeah, I mean, these documents have been shared with Professor Sahula. He will share them with you. He may have already put them in that canvas. Yeah. See, sometimes you can give a different name. So here is a good example. Okay. So there is a signal called W, right? And that is 32 bits. Okay. And then there is another one which is LSB, which is 8 bits, and MSB, which is 8 bits. So the alias gives another name for this W7 colon 0 and W31. Okay. So it's just that you are trying to call it by a different name. Okay. These examples are not so great. This is a better example, right? I don't know why he has complicated with in out and all that stuff. So here, this may be a better example. So sometimes we are trying to give a different name, okay, to the same signal. Okay, so it's a sort of, let us try to take a simple example. I think we can say it here. Alias YLSB equals Y of 0. Okay? And then you can display it here. Maybe I have to put that flower back. Good evening. Let me give a slightly different example. First, let me share this with you. I think he wanted me to share that with you. So let us consider X to be, because Y is a wire, I can't directly assign like this. I can do is, okay. So in this example, all we are doing is we are giving more meaningful names. Okay. So the input came to us as a 3-bit bus called in, and the output was a 3-bit bus. Okay. So it's important that they are wires. Okay. We can't apparently do this for logic, etc. We can do it only for wires. But a good way of giving meaningful names will be using the alias statement. Okay. See, it would have been very complicated to read into, in, one, etc. here. Okay. So it simplifies your, the code a significant way if you can say these are nothing but A and B and C.
Sir,
Any questions here?
sum and save to orders are bit position is 0, 1 or 1, 0.
I'm looking at 2 and 1 as the inputs and 0 as the carry in. It doesn't matter.
Okay.
See, it's
Okay.
a convention.
Yes, sir.
So I could have called it 0, 1, 2. It doesn't matter. But as long as you are clear about which is the carry, which is the input, it's just a convenience they have provided to rename some wires using some naming so that the code becomes a little bit more readable. Okay, that's one advantage of this alias signal. Okay, so that is one thing that may be useful. Another thing that we may not have explicitly done is see, suppose we have module this. See, these are all not for synthesis. No, I don't know. I have told you. These are not for synthesis. These are mainly meant for your verification, right? And why would alias create additional wires? It won't create additional wires. So let us look at an example where we have bit, let us say 7:0, 7, let us say M. So this looks like a static array. So this is a static array where I have 8 words starting from 7 to 0, and they are all each 1 byte. So we could have called 8 byte also. Yes, so byte mem 7:0, or maybe 0:7, maybe more. Sort of. It is more common to think of bytes as 0 to 7, right? It's more. Uh, we are more comfortable reading starting from 0 to 7. Then initial. So we could create a file somewhere. Say call it so let us say we save this in mem.text or something like that. Okay. So yes, this will, I think this. So mem.text now has this stuff. Okay, mem.text has this stuff. So there is a read mem available. Okay. So the read mem is $read mem. Okay. And I think the file name is first, I'm not very sure. Read mem B. Okay, that means binary content.
Very melody. अरे हिमांशु भी तो जाएगा साथ में।
Okay. So we'll try to read this text file. I'm not very sure. I think maybe this first. Okay. Let us try this one, and if it doesn't work, we'll. So, so first the file name, then the array, right? So it read this content. Okay. So it has initialized the memory by reading this content. So 0100 1011 like that. So some application you may require to load bits from some sort of a file, right? And you may want to, simulate something, right? So in such an application, you can use this. So read memb and write memb is the exact opposite. So if you want to write out the contents of an array into a file, you can do instead of read, you can put write. Okay. It will create a new file. Hopefully that file doesn't exist, right? And it will write to that file. So that way you can examine the content of that memory little bit later. And I have a feeling what happened here, why is it last one not correct? Why am I getting 1, 2, 3, 4, 5, 6, 7, 8, 9? Why did I get? Because I have set y equal to 0. Did I not ask for exactly 7 of them? Starting from 0 to 7 only I asked. No? But I think it requires a new line. So that new line is important. So I have to save this file and then yeah, I have given less. Oh, I'm sorry, I have given less here. So this is 1 now. So we have to give 1. Okay. See, there is one more file. I had not given, I had only given 7. My mistake. Okay. So professor who asked me about 0D, if I put 0D, what will happen? See, now that space is gone, no? That white space that was coming. Right? So that is the advantage of that 0D. If I do just D, it will look a little bit less, doesn't look as good. Okay, a lot of spaces. So 0 is a better, by default, it fills spaces. We can also try 0, 3D. Okay. So now it has used zeros to add a 3-digit thing. Okay, so you can read more like this. There are many such formatting things in C language. They have taken all this from C only. Any doubts in this? Not looking at the chat. Let me just get the chat.
Sir, can you try one right also? Or we'll try, sir.
You try, man.
Yes, sir. Yes.
Read maybe instead of that, write you do. That's all. Okay. Okay. All right. So using this idea, you can try writing the code for a very simple, maybe a processor, a very simple processor, right? Which is a, or maybe it's better to say calculator than processor, right? So, so let me explain that here. So let us pretend that we have to do things like 2 plus 3, 5 plus 8, 9 minus 5, 6 multiplied by 4. So a calculator can do these kind of things. Okay. So we'll encode plus by maybe 0, 0, minus by 0, 1, then star by 1, 0, and maybe division by 1. Okay. So division is integer division. It is not complicated by trying to do floating point. So if you are trying to divide 6 by 5, the answer is 1. So it is not going to be 1 point something. Similarly, 14 divided by 3 is simply taken as 4. Okay. Remainder is, we can also, you could have given percentage also as another one, but we need one more bit. Okay, we need one more bit. But right now, this is good enough for us. No, actually, we may need. We'll keep one more operation called store. So what that will do is there is a stack. So when you say store 2, the value 2 will be stored on the stack and the pointer will move here. Initially the pointer was here. Now after store 2, then store 3 will store 3 and move the pointer. Then we can add, we can say add. Okay, like you do in the calculator, right? You will say 2 enter, 3 enter, and then plus. Okay, the same thing. We are saying store 2, store 3, add. Right? So the add will cause these two guys to be removed from the storage, and the plus operator to be applied, and finally you will have 5 on the stack. Okay. So if I need to calculate something like this, so our program will look like this: store 2, store 3, then add. Oh no, it's multiply. Then store 5, store 8, and then add. Okay. Then finally multiply. So what will that do? Initially 2 is stored on the stack, then 3 will be stored on the stack. Then this multiply instruction will cause both of them to be removed, and the product will be stored on the stack. Then we are storing 5 and we are storing 8. When we say add, these two guys will be removed, and addition will be 5 and 13 will be on the stack. Then when we say multiply, these two will be removed, and that will be 64. So that is how this calculator will work, right? And the instructions for the calculator will be store and the value, then add, then multiply, then subtract, then divide, right? And then we can also say retrieve if you want. Retrieve into a register. And we could also try this, but let us leave it to keep it simple. So at the end, we'll display whatever is on the stack. Okay. So this is a very simple calculator. Is it clear to you how this calculator works? We have a stack. Maybe we can decide how many. See, it depends on the depth of that expression. If we write a very deep expression, we may run out of space in the stack. But we'll assume that it won't be like that. See, if I keep on writing like this, 2 plus 5 plus 3 plus 8, etc., long expression, I may run out of space. But if I keep doing plus in between, so if I say store 2, store 3, then if I keep on doing all the stores first and then do adds, then that will run out of space, right? So, but we could do store 2, store 3, add, then store 4, add. This way I will not run out of space. Okay, so that is what we have to do, right? So if you see this program, so we are writing store plus star minus division. We can assume that these are 3 bits. In fact, we have room for a few more instructions if you want. Right? So that will occupy the first 3 bits. And the value is, let us say, the remaining. So we can maybe give about, let us keep it simple. We'll give maybe 5 bits for this. So this is how our memory is stored. So if you want to write a program for store 2, store 3, store 4, then add, then multiply. Then this will be like this, store means 0, 0, 0. 2 is 0, 0, 0, 1, 0, right? And then this is again 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0. Add will be 0, 0, 1, and these are don't guess. Then multiply is 0, 1, 0. And at the end, we could give another called display. That's a better idea. Let us say display. Let us say 1, 1, 1. So 1, 1, 1 is display. Again, this is another code. So this is our program. And maybe we have to give a halt or stop or something. Maybe that can be 1, 1, 0. So it has to go till this. Right? When halt comes, it's stop. Okay. So would you like to give it a try? So let me, make you try and think about this and try your, is the problem clear to everybody? Some people are saying yes. Not sure. If anybody didn't understand the problem, please let me know. What a little bit means, little bit not clear. So we have a memory that will store this program. Okay? So your processor or calculator must start, reading this content and look at what these 3 bits are. If it is a store, it should take these 5 bits and store it on a stack. And then, the same thing for these 2. When it comes across a add instruction, it should remove 2 elements from the stack, add and put it back, and so on, right? So it should execute these instructions. Then if it sees a display, it will display the top of the stack. And then if you see 1, 1, 0, it will halt. So it will keep going like this, okay? See, there is no jump or anything like that. It's just very straightforward. So it's not it's a very trivial, there's no if then else, there is no jump, nothing of that sort. It's a very straight linear execution. So give it a try. I'll be here. Give you some time. The program is in the memory. That is what I explained. No, I told you how you can store the program in a file, the zeros and ones, and then you can read it into the memory, right? That is why I explained. If there is a way, two of you can join together and do, I have no problem. If the system allows collaboration between two, three people, breakout room kind of a thing, I have no problem if you want to discuss among yourselves and do it. Okay, not a problem. Or mute yourself, call your friend and do it together. No problem. This is like a toy calculator. Let me see if anybody has written anything in the chat.
नहीं नहीं यार, ये आज नहीं तो कब से स्टार्ट हो गया, बस फॉर्म फिल करके आ गए।
How is it going? Anybody wants to share their thoughts? This is not supposed to be go for tea break, okay? This is supposed to be an assignment. All right, let me ask you questions. So how are you planning to, let us call this calculator? So let us assume that the memory is, let us create one bigger number. Maximum memory. We can keep it some 1024 or something. 32 is good enough, right? We may not write anything bigger than that. So this is the maximum size of the program that we are. So the program, we can call that program.text. We read the program into the memory. Then what should we do? We should go through the program one at a time. So maybe we can call it for I equal to 0, right? When does the program end? When we get the halt instruction, right? So tell me, what is a good way to represent the instructions? What would be a good way? See, you could try enumerated data type. Okay. Enumeration is a better idea here, right? Enumeration, enumerated data type. Okay. So that must be, let us look at the syntax. See, it will allow you to say things like idle equal to and give the let us try this one maybe, right? So apparently, if you start with bronze equal to 3, automatically the others will become 1, etc. So we can try something like that. I don't know whether you can case by case do. It's also not bad, right? Enum, what are the instructions? We have store, we have add, we have multiply, we have subtract, we have division, add, subtract, multiply, division. Then I think we had halt. What else? Display, display. So these were our instructions. So we can store it here. And if you insist on those codes, I think it will allow you to write 3B000, right? And so on. So that is what I thought he was saying, right? You can give these codes, right? We wanted add to be 001. We can put subtract to be the next one. Null is, let us say, 3B011. You can use case statements, no problem. Let us say this is our instruction. Let us make sure that this syntactically doesn't cause any problem. Then syntactically it's okay. So where is the end calling? It's done because this is a after. Okay, so we read the instruction, right? We could also do it with a while loop, I think. No? I equal to 0 while I less than maximum, right? So it cannot go beyond that, right? Begin end. Then we will fetch the instruction. If this is maybe this is called opcode is a better word. Okay. Instruction is the whole thing. Let us say we get it from mem of I. Okay, we get the instruction and then I is incremented. Right. Then we have to check if instruction, sorry, this is instruction is, let us say, defined as a maybe a logic 7 to or a byte instruction. There is instruction is a byte. So the last 7:7, 6, and 5. Okay. I would have loved to use alias here, but I think it is only allowed for wires. Okay. So unfortunately, this is not a wire. So as a result, I can't directly use that. Okay. So we could say if you want op code equals op equals this. So we can assign the last 7 bits to the opcode, and if opcode equals hard, then we break. That means we don't do anything, we come out. And I think the question was, can we use case here? I think you can use case. Somebody asked, can we use opcode? Can we use case? I think you can use. So the case was hard, we break, right? Then we have store, right? We have store, we have add, etc. Multiply, subtract, divide, display. So if it is displayed, we will $display. So stack pointer we have to keep. We have to keep a stack pointer, and we have to declare a stack. Okay, so stack we can declare to be define stack depth to maybe 8 or something like that. And we can declare stack pointer. Stack pointer will be right? And the stack itself will be bit maybe 5, I think. It's only 5 bits, right? So 4:0 of stack 0 to stack depth. This one. Mhm. So let us go through this again. I have declared stack depth to be 8. That means I am allowing up to 8 entries in a stack. So I will need log 8 bits or 3 bits to address the stack maximum, right? And the stack itself has 0 to stack depth -1. I am going the increasing order. Stack is in the increasing order. And each element of the stack is 5 bits. So initially we will keep stack pointer to be 0, right? So when we are asked to store, we will this display will come back to it. Store means, see, we have already what should we do? We should just stack of sp equals that instruction 4 to 0. Okay. So instruction 4 to 0 contains the data, so that will be stored in stack pointer. and maybe we can increment this stack point. Ideally, you should check whether the stack pointer has exceeded that final value and things like. See, after incrementing the stack pointer, if it becomes 0, for example, that means we have an overflow, right? So we have gone beyond the available memory. So if you want, you can add the check. For add, what should I do? I should remove 2 elements from the stack, add those 2 and push the value back onto stack. So what should I do? Stack, so element 1, let me keep that as a element 1, element 2. Okay. So element 1 or the maybe operand 1 and operand 1, operand 2. So operand 1, where will it be? It will be just above stack point. Stack point has already been incremented, so we should go to this. We should subtract and then fetch. That means we should do stack minus SP. So first subtract the stack pointer and then fetch. Similarly, operand 2, will be also stack minus SP. So I have pushed 2 values, only then I'm. So again, I'm going to assume that nobody will write a wrong program where they have not got enough elements on the stack and they'll try to add. See, in the very beginning, if you put an add, it is incorrect. Okay. So we are assuming that all the programming is correct. So if something goes wrong, nothing can be done. Then we add the 2 values, operand 1 and operand 2, and we put it back on the stack. So again, stack of SP++ equals operand 1 plus operand. All the others will be very similar. Okay, whether it is add, null, etc., we still have to. We could try something like add null subdiv. In all these cases, these 2 have to be done. So we have to take out 2 elements. All our operators are binary operators. Add is a binary operator, null is a binary operator, subtract is a binary operator, div is a binary operator. This end is also possibly not required. No, it's required. So take out 2 elements. And then maybe we can write another case statement. For add, we have to stack of SP plus plus equals operand 1 minus plus operand 2. Sub is the operand, maybe it should be operand 2 minus operand 1, because the first element would have gone first. Okay, so operand 2 is actually the first element. Similarly, null is stack of SP plus plus equals operand 2 multiplied by operand. See, again, the assumption is that the multiplication will fit in 5 bits. The product will fit in 5 bits. So then we can go ahead and division stack of SP plus plus equals operand 2 divided by operand 1. Then there may be a default, that means none of these are there. Then we should display illegal instruction. So once again, so we declared this is an instruction memory. Okay, this is mem is actually instruction memory or program memory. So maybe it's better to call it program memory. And we are going to get it from program, right? And stack is stack depth. This should be called program memory, right? Then we have an opcode which is 3 bits, and we are storing. I mean, we are indicating that store is 000, etc., etc. Right? And we have 1 byte to get the instruction. So this is a so-called instruction register. Then stack is 0 to stack depth minus 1. Then operand 1 and operand 2 are both 5 bits. So it may be better to declare 5 def bit 4 to 0 to be number. So that here we can just call it number. Then so stack pointers set to 0 in the beginning, right? And then we read the memory. We set the this could also be called program counter if you wish. Okay, the program counter. And a program counter code is the initial 3 bits. That is our opcode. So then we check the opcode. If it is hard, we break. If it is display, we whatever is the one before the stack. See, the stack pointer would have been incremented. So we should display whatever is, ideally we should pop and display. Store is, we just store the number. Then add multiples of div, we just first we do these two for all of them. Then further we go and check whether they're added on the perfect operator. Then if it is none of these, then we. So in this example, we can start by storing, let us say, to store three. And I think it allows these kind of comments are allowed. Store 4. Then let us say we perform multiplication. So 4 and 3 is 12, so it will fit in 5 bits. Okay. So let us try multiplication. These are don't care. So we just say mul. Okay. So 3 times 4 is 12. Let us say to that we add 2. That means we add. So now we have performed these guys, and then maybe we can store one more value. Let us say we store 14, right? That is 0. Um, then we can do a subtraction. Subtraction is 0, 1. So the answer should be 0. Okay. The last two values are not important. So we don't, this is, halt is required. Halt is required. So halt is 1, 1, 1. And maybe before that we could have displayed. We are just tight. Exactly 8 values. Of course, we have more. 32 is allowed. So when we read only 8, the others will be read as possibly zeros. Okay. So when we read the remaining, see there are only 32. I mean, this allows up to 32, right? And we have only given 8. So it will initialize the rest to zeros. Okay. So we can give this a try and see. Enumerated data type is thousands and format. Oh, this has to be made a new bit like this. We have to write. Okay. So we have to write a new bit 2 to 0. So if you don't do that, I think it doesn't know how many bits to keep and all. Oh, program text itself is not there. You should have named it or program.text now. You see, the answer has come. The 0 is there. Okay. But let us verify that it's right answer. See, let us instead of sub, let us put the add. Okay. It should give me 28. What is add? Add is 001. So 0 is dangerous. It may write 0 for anything. Okay. So this is okay. 28 is there. Let us try. Instead of this, let us try div. Okay. So let us try 4 divided by 2. 4 divided by 2. Okay. And oh, sorry. This should be 4, I think. This is store 4. Then store 4 again. Then store 2 again. So now if I divide, I'll get the value 2. And then 2 and 4 are being added. So that makes it 6. Then 14 and 10. This time I expect 20 to come as the answer. 26. Let's see. We stored 4, another 4, and then 2, and we did a div. So 4 divided by 2 is 2. Then we are adding 2 plus 4 is 6. 6 plus 14 should have been 20, no? Why am I getting 26? The division is it doing the way we think it should do? Suppose I multiply, then 4 times 2 is 8, then 8 plus 4 is 12. Then it should have, maybe I forgot here. No? This div I forgot, I think. It should be 100. It is acting like a now it makes sense. So if you want div, I forgot to change it here. Okay. So let us make sure that these are all correct. 0 is stored, then 100 is div, then add is 001, then store, then add. Okay, so this time I'm expecting 20. So I think it's okay, right? So was this useful? Did you understand this? Those small warnings that I'm getting, we have to go and see what is the reason for those warnings. See instruction 75, most significantly bits, it says this assignment is a violation of system Verilog strong typing rules for enumeration data types. But instruction is not an enumerated data type, right? Instruction is a ordinary byte. And I'm just extracting the first 3 bits. This opcode equal to is causing a problem. See, they are saying this is a violation of your, you see, opcode is a 3-bit number. It is doing it, but it is complaining that it's a violation of, on the left hand side, you have an enumerated data type, and on the right hand side, you have a 3-bit number, and I think they are not comfortable in doing it that way, but it is still doing it okay. All right. Any other doubts? Anything that I can clarify? Line 22, it is mem.text. Line 22. See, I changed it. Okay. Or maybe he was trying to tell me that I made a mistake. Okay. Thanks. And the rest of the bits of the instruction. I is like program counter. Yeah, that's right. Anything else like this? I'll save this file. You can try if the illegal instruction correctly comes. It will come. I mean, but just to be on the safe side, you can try all those things. Anything that you could not follow?
Sir, can you show the contents of the entire stack after the program is executed?
Yeah, I mean, you can just print out the entire stack. Yeah. It will have all those numbers will still be there. So this is the stack content. Is it correct? The stack depth was defined as stack depth was defined as 8. No, why am I getting so much output? Stack should have been only exactly 8 things. No? No, no. Oh, what happened here? Something is wrong. Can you tell me what is the problem? There is a very subtle problem. Very important subtle problem. Tell me, who will tell me what the problem is? See, that's a clue. See, he ran out of. That's a clue. So tell me why.
With respect to end position,
Huh? What is the answer?
the for loop is not in the right place. So
No, no. For loop in the right place. The for loop in the right place. You can see. Why is it going on and on? There is a very interesting problem. No, not stack depth -1. You can see, maybe the clue, the hint is here, somewhere here. I won't tell you exactly where. Why overflow? What is the reason? There is no overflow. Stack is fine, no problem with the stack. There is no overflow as such. Tell me what is the reason. That's correct. I think Dave has got it correct, right? So the answer is, see, we defined the stack pointer to be 3 bits, right? So the only numbers it can hold are 0 to 7, right? And the termination condition is it should stop when it becomes 8. It will never become 8. Okay, when we from 7, when it goes to um, 8, it actually becomes 0, right? So it will always forever, it will do this forever, right? So what is the fix? We can try to make this slightly higher. You see, we can make this 1 bit extra. So avoid this -1. Okay. Then it will have a chance to go to 8 and it will stop. and you can see the contents. So this is, I think, what we printed 20, right? 14, and all those guys are still there. That make sense? Does it make sense?
Okay, sir.
Okay, so good. I think I'm glad that you guys got that. Anything else? Okay. Yeah, I mean, why are you insisting that I should not define? See, it's a good thing to do. See, in this example, see what he says is if bronze is 3, then this will automatically become 4 and 5. Okay. But it is dangerous to depend on all those things because tomorrow my opcodes, if I rearrange, everything will go wrong. Okay. So it's better to explicitly give the opcodes. Okay. It's very dangerous to rely on these defaults and say that, see, tomorrow maybe the person who wrote the code may not be constantly taking care of this code, right? Tomorrow he goes to another project, and then somebody else comes and they don't know. So they simply say, why it's starting from 3, let me make it 0. Then everything will fail. And debugging that would be hell, right? So it's better to, in this example, okay, in any case, even in, see, normally we don't even care. Normally we don't care about what states it assigns. Okay, let it assign anything 0, 1, 2, whatever it is. But in this case, we care. Why? Because our file preparation is based on this, isn't it? If we can't change these values, see if we rearrange these things. Suppose somebody comes and adds another instruction and they put it in the beginning. Then in your method, everything will change. In program.txt, we have coded 100 as something. So all that will fail, no? It's clear to you? So don't rely on all those defaults. See, defaults should never be relied on because it works for you, but small change, everything will break down. Okay. So in the industry, they will keep on emphasizing that don't rely on defaults. Okay. Can you redo this using class as an exercise? Do the same thing but use class and see how it works. The exercise is do the same thing with class. Redo the stack calculator using class. You are welcome to define as many classes as you want. Okay, that is the exercise. So think for some time. Okay, and And you guys are telling me now that I'm not audible. Huh? Sorry. So I have been experimenting with class, right? So memory is a class, and inside the class I have declared progmem to be a dynamic array of bytes. And the new function simply initializes that progmem. Okay, it's a dynamic memory. So here we are doing the allocation for that memory. Size is an input to that progmem. Initialize takes as input the file name and performs a read memory. Read mem is another function which takes an address and returns the corresponding byte. And we are giving a dump which simply dumps all the content. Rajesh, Sevugan Rajesh, please mute. Rajesh, Rajesh. So did you guys follow this memory class? And in the main program, we can assign a class called memory, right? And call it pmem. And we can initialize pmem equal new, let us say max size. So we have already declared max size to be 32. So this is the size of this memory. Hey Rajesh, man, you have to really turn it off, man. Rajesh. If you have that guy's number, you can call him. So this could be our simple test for the memory. Okay. So we Okay. So the initialize takes a string called program.text, but rename doesn't seem to be doing correctly. Was that file name called program? It's gone now. Oh, nice. So it has been initialized. Okay, so our memory class is okay. Any questions here about the memory? You can have a class called maybe CPU. So it will have an enumerated data type. This enumerated data type is causing a lot of headache. Even this very long, see, this guy causes a lot of problems, man. His ICAR is very long. He doesn't understand this. He is giving a lot of errors. At 14. So sometimes your ICAR is very large, you have to Don't support dynamic memory is what I'm beginning to expect. But he didn't give an error here. See, he's not giving an error there, but he's not willing to take this. Sorry, we'll have to, if you are doing Icarus Verilog, you may have to use the old way. Okay, you'll have to do max size. So this is not required. In Icarus Verilog, nothing. New is not doing anything great. Okay, new may not even need it. And any idea what is wrong? This read may be worked now. Earlier we had made it work.
Now, should the file name be in quotes?
File name. Well, the problem seems to be here. Is read
Should
may
it be
be.
in quotes? Should it be in quotes?
That is only here. See, here I have given in quotes. So file name is a string. So that is okay. See, it is writing. Earlier it was doing no. I think when I did this, there was no problem. Expecting one to index the property problem. See, this is, I think, not a. No, man, that is not the thing. He's saying it should be from max size to 0. No, no, that doesn't matter. Even if I change this, it will not change. Okay, they think that this is the reason. No, it won't be the reason. It is saying something like, I got 0 indices expecting 1 index to index. So he's saying you cannot directly refer to problem. You have to index it with something. Okay. But that's not the way this read memory works. Okay. So that's the problem. 4. 54 is, this is not correct. It's not what. See, core dump because I am giving program memory of 0. So that is not correct. Vicarious Verilog has some difficulties. So one possibility is, unfortunately, we'll have to apply this outside, which is very silly. See, when you declare it outside, it understands. Okay. But when you declare it inside, this guy doesn't understand. So there are some limitations like this. Okay. In memory, you see, this class, the program memory should be part of the class, not outside. But there is a limitation here. So you can do like this, move it into memory class if you have access to cadence or other commercial scripts. It is moved here for making high very low is very low. Okay. So the ideally when you say class, the data is encapsulated inside. Okay. And then so now I think it may be okay to do this. Since we are doing it outside, it may not mind this. Let me try that. No, this new thing doesn't. Oh, sorry. See, it doesn't understand this. So you have to do it that way. So you should be aware of these things, okay? So that if you are working with a simulator that doesn't support, you should at least get it to work. Is that clear? So what is the CPU? What is its job? Maybe we'll require an opcode for instruction, okay, which is a byte, right? And then it requires a stack pointer, which I think is okay. So stack is inside the CPU. Okay, so we'll define. Again, unfortunately, stack may have to be defined outside. Huh? I'm not sure. We may have to define it outside. Not happy with that solution. So stack is a bit. Let us declare number to be a bit 4 to 0. and we can try and say number stack 0 to max stack. We'll try. If it doesn't work, we can always go back. So we have declared the instruction. We have declared the, maybe we need an int called program counter. It can also be we can size it. We don't have to have a full integer first. We can make it log, etc. Then what are the things that we can do? We can maybe, fetch an instruction or initialize. So the initially EC is equal to 0, right? And stack pointer is 0. Stack pointer should be, let us keep it as int only. So these are the initializations we can do and then what else do we do? We can fetch an instruction. And fetch from where? We have to fetch it from a specific memory. So let us say that mem is given here. And it will say return mem of PC. And PC will be implemented. So it's a very trivial thing. Then execute. We have fetched. We have execute. So here you have to do the actual execution case. So let us take the 3 bits, bit 3 to 0, I'm sorry, 2 to 0 of code. Opcode equals instruction of instead of return, we can just do instructions, and we could make this a task. It just puts the instruction into that INSTR. So we'll take out the last 3 bits of the instruction, 7, 6, and 5. Then do case of 4. Okay. So 3B000. We are not going to do enumerated data type because this guy has a lot of problems with it. So here we just store, right? We are going to store the value. So what do? We say stack of SP++ equals instruction of 40. 3B001 is add, and 3B010 is subtract. 3B011 is possibly div, right? 3B, 100. In all these cases, I have to go and fetch the two operands. So we'll declare operand 1 and operand 2, right? Then we'll say operand 1 is instruction no stack minus minus system. Operand 2 is stack minus minus 60. So we fetch two things. And again, depending on operator, so this is store. So we will no, this is 001 is add. So we simply stack of SP plus plus equals operand 1 plus operand. So this is our execute function, and I think we have to also handle halt, etc. Halt is 111, I think. So there we don't do anything. We sort of dollar display done. Okay, and 3B once displays 111. So we'll have to fetch the stack value number result, and result equal to stack minus minus SP and display plus VLSI. Okay, so it displays the result and then end. So that is what we do for display. Okay, so I think that is all we had, right? All the store has been handled. Everything else has been handled like this. Okay. It will make sure that this works. Oh my God. 53. 53. Number as it defined somewhere, type left. Forty-one is where the problem is. 41. 41. Asked by Fetchman. So this is 66 service syntax. It will end, I think, this year. So this end should be here. No beginning. It is so what do we do? Suppose let's say in person still so it has no problem in fetching the operands, but when I store it back, it is complaining. Why? Okay, maybe I will do it like this. I will say result equal. Okay, result equal to cases. We will go ahead and stack of SP++ equals. Let us try this examples. 160. Okay, number result cannot be declared like this. We have to declare it here. Okay, it should not be declared in the middle like this. 42 cannot select part of scalar mem. Okay, we have to say what is mem? Mem is a memory, right? So we'll have to say number. What is it? Mem is what is the size of mem? Mem is byte. Byte. What is a byte? Mem max 0 to max is. That was a mistake. So this is a bit what to do. 41. Sorry, subroutine ports is unpacked dimensions are not yet supported. Oh gosh, never mind. So fetch means just fetch. Let us not do anything. Okay. Instruction is none piece of this piece. Does it work? We have declared mem as what? Prog mem. Prog mem. So I should call it prog mem. Line number 42. So there are some limitations in this case. Okay, at least this much it is got. So it is compiled and gone through. And why is it failing here? Because in the dump part it failed. Huh? Interesting. What is pmem.dump? Pmem.dump will write memory dump. Okay. Pmem.new. Oh, okay. So this reading didn't count. So obviously it has aborted at 82 before 82. So what is it? It gave up here. This initialize it gave up. That should not have happened, no? Because I have defined this outside. There's no problem here. Hmm. This bad. Okay, instead of initialize directly reading it will work. So it failed in new, is it? Amen. Hmm. Something else is wrong. understand why it's like it's memory payment. Nothing is coming. It's not even going there. Even the starting is not coming. Something happens. What is 11 about it? What does it mean? 11 is what? It can't be. Oh, yeah, it is just only. Mm. I'm not very sure why it is giving up. Okay, sorry about this. The others will work. I'll have to see my like I don't know why it is giving that one. Mm. And once you dump the, let us say this is not required. We don't need to dump the data. This is more of a sort of verification. Okay? So this cadence will do this also. It will not have any problem in initializing inside also. It will not have any. So we are allocating memory to the, we are doing a sort of creating an object of the type memory. Then we are initializing that memory by reading the content from the file. Then we are dumping it for verification. Now we will have one more called CPU. And let us say, you know, stack CPU or something. So we have declared stack block, right? And then we declare that also to make sure that this goes through. So then stack dot where to stack dot fetch has to be done. Stack proc dot fetch. Okay, that will fetch the instruction. Then we have to check if it is while while we fetch, and if stack proc dot instruction equals halt, then we stop. Okay, if it is not, and keep not done equals true, while not done. And then if this is true, then not done is 0. Okay. Otherwise, stack proc dot execute. So that I believe will fetch all the instructions and execute. Okay. And at the end, we can see, we got the 12, right? 20 has come. Right? What was the error it gave? This is not instruction. It is 3 to 7. I think by mistake our execute is a function, so we have to change it to a task. So execute is a task. So I think we got the same answer, right? So we can try null here. No, I'm sorry, this has to change. Null is 0 1 1. I think. So we got the same answer, 26. So 4 times 2 is 8. 8 plus 4 is 12. 12 plus 14 is 26. Right? And we can try subtract also. Subtract is 0 1 0. Right? So I'm not sure how it will work. 12 minus 14, what it will do? 12 minus 14, it is writing it as 10. Okay, because of the overflow. Okay, so the answer is not exactly correct. We can try increasing the number a little bit, maybe 3. So 12 plus 4, 16. 16 minus 4. So this is 4 plus 3. 4 times 3 is 12. 12 plus 3 is 12 plus 4 is 16. 16 minus 4 should be 12. Correct. Once again, this is 4 and 3 multiplication. 0, 1, 1 is multiply only, right? 0, 1, 1 is multiplication, yeah. 4 times 3 is 12. And then 0, 1, 0 is, oh, this is subtraction. Sorry, this is subtraction. So we are doing, still not working. So maybe we can change it to 16 here. So this is 16, I think, right? So 4 times 3 is 12. 16 minus 12 is 4. So this time I should get 18 as the answer. So if you get negative, then it won't work. We have not signed, we have not handled sign, etc. correct, right? So that you can fix, right? So let me quickly go through the whole thing. Okay, I think there are a lot of, it is still not working on Icarus. Okay, it is working only on Cadence simulation tool, because looks like it has some limitations on classes, right? So as before, we have declared the size of the memory to be 32, right? So this is the size of the memory. This is the size of the stack. So each entry in the program memory is a byte, and we had to move it out here because this Icarus doesn't support. Okay, but in Cadence we are welcome to move it here. Okay, we can move it inside the memory. That is the correct way to do it. Okay. And they have declared a type called number, which is a 5-bit number. Then this stuff, etc., we don't need all this. Okay, it was a test to see. We don't need all this. And unfortunately, this guy is not working for us, right? So this. Then initialize takes a string and using that as a file name, reads the memory and initializes this one. Okay. So in Cadence, you can move this to this state. Okay, you can move this memory statement inside memory. Okay. Then we have written a thing called read man. Okay, this was not required. We didn't. I don't think we used it. Maybe we did. Maybe we did. So read memory will sort of return. Did we read memory? No, we are doing directly. Okay, we should have ideally said read mem. Okay, we should not say program mem PC++ ourselves. That is what this guy is supposed to do. Weidman is supposed to do. So ideally, we should have done that. Okay. But we have sort of gone ahead and directly used it. Okay. So that's a bug. Bug means it's not a good practice, right? Then dump is just for verification. CPU is a class. Inside the CPU, we have an instruction register, we have a stack, we have a program counter, we have a stack pointer, right? In the new function, we initialize all these guys, we fetch the instruction, right? Okay, and then we execute. This is the usual stuff. Okay, what is not a good idea is this 3B11, etc. It's we should not hardcode. Ideally, we should declare them here. So define halt to B3, B011, etc. So this is what we should do. And we should use halt there instead of, okay. Otherwise there will be a problem. Problem meaning bugs can easily occur. Okay, so I will let you do. Any doubts? What are the doubts? Sir, indexing, it will be from big to small. Yeah. Sir, if SP codes are not synthesizable, then these designs are better to make in C or other language. See, the thing is, there may be other advantages. We have not seen some of the other things that we have in system Verilog. The coverage. See, we have not talked about functional coverage yet. Okay. So if you want to do things like that, you will have to use system Verilog. Okay. If your interest is only in um, verifying something like this, I agree with you. We could have done this in C language or any other language, right? But if our interest is to get coverage information, right? For example, I may want to know how often is stack overflow occurring, or how often does a particular instruction get executed, or things of that nature. Then I may have to use these tools like the Verilog has built-in tools for all those things. System Verilog has, a lot of concepts which are oriented towards verification. Okay, so that is where you can't beat. Okay. What is no sir? I don't know what no sir means. No doubt. Okay. Any other doubt? Okay. So I'll give you this code also. This is the code for the class based. So the thing is, it is not fully working on our, this must be, doesn't fully work on, at present, it will not work on Mac as well. Okay, so we'll have to see what could be the problem. All right, I'm sorry I took a few minutes extra. Any doubts before we close? Attendance is not updated, but I think the organizers will take care of it. B. Radha, no sir. So you can modify this to do some more things, right? This CPU definition can be modified, do many other things, interesting things. Right? I'll let you do that. All right, guys. I'll see you tomorrow then. Bye.
Yes, sir. Thank you, sir. Good night.